It's amazing to think that everything around us, like from the strength of a steel beam in a building to the fizz in your soda, it all comes down to these like really basic building blocks, the chemical elements.
Yeah, it really is incredible, isn't it? And you've given us some great sources to dig into all this foundational stuff.
You're right. We're going to be taking a deep dive today into the periodic table of elements.
That's right. And we're also going to look at how these elements combine and the essential rules for how they get their names.
Yeah, it sounds complicated, but we're going to break it all down. Our mission today is to really pull out the most valuable insights from the material you've provided and try to make sense of how this really kind of amazing chart organizes all the matter that we know.
And how chemists actually talk about these substances that are formed from these elements.
Exactly. Okay, so let's just jump right in, shall we? The periodic table. When you look at that iconic chart, what is it actually telling us?
Well, at its core, the periodic table is a very systematic way of arranging all the known chemical elements. And the fundamental organizing principle here is the atomic number, which is the number of protons in the nucleus of an atom of each element.
Right.
And what makes this table so powerful is that elements with similar chemical behaviors end up being grouped together in this arrangement.
So it's almost like a cheat sheet for how things are going to act.
Yeah, that's a great way to put it.
Right. And this wasn't always the way it was laid out.
Right.
We learned a bit about a scientist named Dmitry Mendeleev.
Yeah.
What was his contribution?
Well, Mendeleev, back in 1869, he's really considered the originator of the periodic table. His brilliance was that he arranged the elements that were known at the time by their atomic mass.
Oh, okay.
But what was really insightful was he actually left gaps in his table.
Oh, wow.
And these gaps predicted the existence and properties of elements that hadn't even been discovered yet.
That's incredible.
It is. Gallium is a classic example of an element that he actually foresaw. Yeah. The material you shared points out that while Mendeleev used atomic mass, the modern table is actually organized by atomic number.
Okay.
And this gives us an even more accurate grouping because it's based on how these elements behave chemically.
So it's been refined over time, basically.
Exactly. And it's fascinating that this even ties in with what students learn in grade 9 CCAP-PS Natural Sciences under matter and materials.
So it's all connected.
It is.
So we have this table ordered by atomic number.
Right.
How do we navigate it? It's this grid of boxes. Well, what do the rows and columns actually tell us?
Okay. So think of it like a very well-organized map.
Okay.
The vertical columns are called groups, and these are key because elements within the same group share the same number of valence electrons.
Okay.
Now, valence electrons are the electrons that are in the outermost shell of an atom.
Got it.
And it's these electrons that really determine how an element will interact with other elements.
Okay. Right.
And that's what leads to those similar chemical properties we were talking about.
So same column, same group, similar chemical behavior because of these valence electrons.
Precisely.
Can you give me some real-world examples of this in action?
Absolutely. So let's look at group 1, the alkali metals.
Okay.
Elements like sodium and I are known for being highly reactive.
Okay.
You know, one of your sources even describes sodium exploding in water.
I do remember that, yeah.
A very vivid illustration of how reactive they are.
Wow.
Yeah. Then, if we jump over to group 17, we have the halogens, like chlorine, Cl. They're also very reactive, but unlike the alkali metals, they're nonmetals.
Oh, okay.
We use chlorine as a disinfectant, which is a very common example of its reactive nature at work.
Yeah, that makes sense.
So you've got reactive metals on one side, reactive nonmetals on the other.
Right, okay. What about the far right side?
Right.
Those always seem like the quiet ones in the chemical world.
You are spot on. So that's group 18, the noble gases.
Okay.
These are the opposite of reactive. They're basically inert, unreactive. Exactly. Think of neon Ness in glowing signs.
Yeah.
That stability is what allows it to glow so brightly without reacting with its surroundings.
Okay, so vertical columns are groups, similar behavior because of those valence electrons.
Yeah.
Horizontal rows, those are called periods, right?
Correct.
What information did they give us?
Each horizontal row, or period, it shows us the addition of a new electron shell as you move down the table.
Okay.
And as you go from left to right across a period, the atomic number, it increases by 1 with each element.
Oh, okay.
So this gradual change in the electronic structure across a period actually leads to predictable trends in properties, like how readily an atom will gain or lose electrons.
So groups are about similar kind of reactivity.
Yeah.
Periods are about trends in properties as that atomic structure builds.
Exactly.
Now, a lot of versions of the periodic table use different colors for different sections.
Right.
Our source mentions a color-coded table.
Right.
What do those blocks of color generally represent?
Yeah, so those colors typically distinguish the three main categories of elements based on their broad properties.
Okay.
So first you have the metals. They generally have a shiny appearance. They're really good conductors of heat and electricity.
Okay.
And they're malleable, which means they can be hammered into different shapes.
Right.
Familiar examples are iron, Fe, and gold.
AU.
Right. We rely on those metals for all sorts of things.
Exactly.
For structure and for conductivity.
Yeah.
What's the contrasting category?
That would be the nonmetals.
Okay.
They generally have a dull look. They're brittle rather than malleable.
Okay.
And they're poor conductors of heat and electricity. Think of oxygen, O, or sulfur, S.
Right.
They're good examples of nonmetals.
And then there's that middle ground, right?
Yes.
Some characteristics of both.
Exactly. Those are the metalloids, sometimes called semi-metals. They kind of exhibit a mix of the properties of both metals and nonmetals.
Okay.
And a key feature for many metalloids is their semiconductors.
So they conduct electricity better than nonmetals, but not as well as metals.
Okay.
So silicon Si, which is essential in all of our electronics,
Right.
and boron B
Right.
are good examples of metalloids.
Okay, the periodic table is becoming a lot more clear now.
Right.
So it's this incredibly organized system that shows us these fundamental building blocks and how they behave.
Right.
But we know what the elements are, but how do we name them when they join together to form everything else in the world?
Right.
Let's get into naming compounds. And you mentioned this being part of the CIPS curriculum, so it must be pretty important.
Yeah, absolutely. It is.
Yeah.
Knowing how to name chemical compounds is really like learning the grammar of chemistry. And your source nicely broke it down, starting with binary ionic compounds.
Okay.
So these are formed when a metal chemically bonds with a nonmetal
Right.
through the transfer of electrons.
So metal plus non-metal transfer of electrons. Got it.
Yeah. And what's the naming rule?
Lay it on me.
It's really straightforward. You just say the name of the metal first.
Okay.
And then you take the root of the nonmetal's name and add the suffix iodide.
Simple enough. Let's see some examples.
Okay, sure.
Put it in practice.
Yeah.
So take sodium, a metal from group 1 that readily loses an electron, and chlorine, Cl, a nonmetal from group 17 that readily gains one. When they combine, you get sodium chloride, NaCl. And as your source points out, this is just common table salt.
That's wild. Yeah, I never thought about it like that.
I know, right?
So,
Okay, another example is magnesium, Mg, a metal that loses electrons reacting with oxygen, a nonmetal that gains them, to form magnesium oxide, MgO.
Okay. So for these metal-nonmetal pairings, it's metal, root of the nonmetal, iodide.
That's it.
Got it.
Simple.
What about compounds that are formed just from nonmetals? You talked about covalent compounds?
Yeah, so covalent compounds involve nonmetal atoms sharing electrons to achieve stability.
Right, okay.
And the naming convention here is a bit different.
Okay.
So we use prefixes.
To indicate the number of atoms of each element present in a single molecule of that compound.
Okay.
So these prefixes include mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and so on.
So prefixes to show how many of each nonmetal there are.
Precisely.
Makes sense in these sharing scenarios.
Right.
Can you give me some examples using those prefixes?
Yeah. So carbon dioxide, COG, is a perfect example.
Okay.
So the prefix D tells us that there are 2 oxygen atoms.
Okay.
And while it would technically be monocarbon dioxide, we usually omit the mono prefix for the first element in the name.
Okay.
So it's just carbon dioxide, 1 carbon, 2 oxygens.
Okay.
Another one is dinitrogen pentoxide, NOO.
Okay.
So D indicates 2 nitrogen atoms, and penta indicates 5 oxygen atoms.
So 2 N's and 5 O's.
Exactly.
Got it.
So prefixes are the key identifier for covalent compounds.
Right. But I noticed in our material that there were a couple of exceptions, water and ammonia specifically.
Why do they get a different naming approach?
Well, water, HO, and ammonia, they're both definitely covalent compounds because hydrogen and oxygen and nitrogen and hydrogen are all nonmetals.
Right.
However, their common names, water and ammonia, are so ingrained in our language and in chemistry that their systematic covalent names, dihydrogen monoxide and nitrogen trihydride, are very rarely used.
So sometimes historical usage trumps the rules.
Exactly. It's a good reminder that, yeah, sometimes common names just take precedence over strict naming rules.
That's a good illustration
Yeah.
that even systematic approaches have those exceptions.
Exactly.
You also mentioned a helpful flow chart in the sources for deciding how to name compounds.
Yes.
It sounds like the first question is whether or not a metal is present.
Yeah, you got it. So that's the first decision point. Is it a metal or non-metal?
Okay.
If you have a metal and a non-metal, then you're likely dealing with an ionic compound and the "-ide" suffix.
Got it.
If you only have non-metals, then you're looking at a covalent compound. And you're going to need to use prefixes.
Okay. And our material also talked about predicting compound formulas.
Yes.
So that's like working in reverse, right?
Right.
You know the name, you have to figure out the chemical makeup.
Exactly.
Okay.
So if you understand the typical charges that ions form for ionic compounds, or how those atoms are going to share electrons in covalent compounds,
Okay.
you can actually predict the formula of the compound they'll form.
Interesting.
So the source gives a good example of aluminium, Al, reacting with oxygen to produce AlRO, aluminium oxide. And this prediction relies on the fact that aluminium usually forms a +3 ion and oxygen a -2 ion.
Okay.
And then those charges need to balance out in the neutral compound.
So understanding the tendencies of the elements helps us predict how they'll combine.
Exactly.
Okay. Now, there was something in the material about a common misconception that all compound names end in "ide."
Yeah, that's a really important one to clarify.
Yeah.
So the "-ide" suffix, it's only for binary ionic compounds. The metal plus non-metal combinations that we were just talking about,
Got it.
it doesn't apply to every single chemical compound,
Okay.
as we saw with covalent compounds like carbon dioxide and dinitrogen pentoxide.
Yeah.
Prefixes are used instead to show the number of each type of atom.
So important distinction.
It is, yeah.
Okay. So we've covered how the periodic table is organized
Yes.
and the fundamental rules for naming ionic and covalent compounds.
Yeah.
But why should any of this matter to our listener?
Right.
What are the connections to the real world?
Well, these basic concepts are really the foundation for so much of what we see in the world around us.
Yeah.
So let's think about table salt, NaCl again.
Okay.
Your source points out that its uses go way beyond just seasoning our food.
Right.
It's crucial in medical applications and in all sorts of industrial processes.
Yeah, that's true.
Or think about carbon dioxide, CO.
Okay.
It's essential for photosynthesis,
Yeah.
which sustains plant life and produces the oxygen that we breathe. But it's also a major greenhouse gas, and it's playing a huge role in our climate.
So even these simple compounds have a pretty big impact.
They do.
Yeah.
So that kind of dual nature of something like covalent really shows how complex even basic chemistry is.
Yeah, it does.
And it highlights how understanding this stuff can help us really engage with these important issues.
And this isn't just abstract knowledge,
No.
right? People have actual careers based on this.
Absolutely. So as your sources mentioned, chemists and material scientists, they rely heavily on the periodic table and those principles of chemical bonding that we were talking about to design new medicines.
Really?
And to develop new materials and create all the technologies that shape our lives.
Okay. So whether you're just curious about the world
Yeah,
or maybe considering a career in science, this basic understanding is really important.
it is.
Okay, let's do a quick mental review.
Okay.
Your source had some quick quiz questions.
Right.
First up, why is the periodic table called periodic?
So the answer lies in the fact that elements' properties actually repeat.
Okay.
So as you move across the periods, or the rows of the table, the chemical properties of the elements recur in a predictable cycle.
Oh,
So it's that repeating pattern
makes sense.
that gives the table its name, periodic.
That makes a lot of sense. Second question, name the compound Cabarrot.
Okay, so calcium CaFO is a metal from group 2, and bromine, Br, is a nonmetal from group 17.
Okay.
So this forms a binary ionic compound,
Right.
and we use the "-ide" suffix, so
Right.
it's calcium bromide.
Calcium bromide. Okay.
Yeah.
Your source also highlighted some keywords from the TAPS curriculum. Valence electrons, reactivity, and chemical bonding.
Yeah.
Why are those terms so important?
They're really the foundational pillars for understanding how matter behaves.
Okay.
So valence electrons are the outermost electrons that we were talking about. They dictate how atoms interact with each other.
Okay.
Reactivity, that describes how likely an element is to undergo a chemical change. And chemical bonding is the process by which those atoms actually join together
Okay.
to form molecules and compounds.
Makes sense.
So yeah, if you understand those three concepts, you really unlock a deeper understanding of chemistry.
Okay. And to encourage some active learning, your source has a self-check exercise.
Okay.
So the first part is about looking at a periodic table.
Yeah.
It says, circle a metal, a nonmetal, and a metalloid, and highlight group 1, the alkali metals, in red.
Okay.
So this is a good way to reinforce those categories we talked about.
Yeah, absolutely.
The second part asks you to name two compounds, KCl and PO. What are the
Ooh.
correct names for those?
Okay, so for KCl, potassium K is a metal, and chlorine Cl is a nonmetal. So following the rule for those binary ionic compounds, the name would be potassium chloride.
Okay.
And for PO, phosphorus P and oxygen O are both nonmetals, so we use the prefixes to indicate the number of atoms.
Right.
So that one would be diphosphorus pentoxide.
Diphosphorus pentoxide. Got it.
Yeah.
So your source wraps up with a really enthusiastic final thought.
Okay.
The periodic table isn't just a chart. It's the ultimate cheat sheet for understanding matter.
I love that.
After this deep dive, I can really see why.
It's true. It's an amazing tool.
Yeah?
Organizes all those fundamental components of, well, everything.
We hope this deep dive has given you a better understanding of the periodic table.
Yeah.
And the basic rules for naming those compounds that these elements form, all based on the great material you shared with us.
Absolutely.
Now, to expand on the periodic table being this ultimate cheat sheet, consider this. How might understanding these properties of elements help us solve some of the world's biggest challenges?
That's a great question.
Like, how could we develop sustainable energy or even create life-saving medicines?
It really makes you think.
What new questions do you have about the building blocks of our universe?